scans it and converts it into a 3D model that you can use. Why do you need a 3D scanner? Let's say you're interested in 3D printing. In order to print a model, you need a 3D mesh. To get a 3D mesh, you need to either know how to use CAD, or you need to scan it using a scanner. So let's say you woke up this morning and you had $3,000 to blow. You could buy a 3D printer. You just jump on the internet, it comes to your house, assemble it, and it's done. It's ready to go. Now, say you woke up this morning and you wanted a 3D scanner.
Wait, did you forget to have them?
No. These are your choices. There are, however, some software options out there. First, there's Autodesk 123D Catch, which is photogrammetry based. Photogrammetry is basically taking pictures of an object and having the software mold it together. David Laser Scanner is a laser scanning system which uses a line laser and calculates the deflection of the laser in order to come up with a model. After it comes up with a mesh, it also takes pictures in order to provide color. So after you scan the model completely, you'll have an accurate mesh with color detail of the model. So why do we do it? Again, say you need the 3D model. What can you do? You can go into Creo, you can go into SolidWorks, you can go to Inventor, but say you want to model an apple. How difficult is it to make the curves? To make a solid 3D apple, when you can just scan it in maybe 10, 20, 30 minutes. There's a huge, huge market out there. The 3D printer market is booming, but nobody has really focused on the 3D scanning aspect. So we hope to one day sell this product to the end user for cheap, easy to use, and it's ready to go.
So now that we saw the current state of what's out there software-wise and our intentions, let's talk about what can you buy if you could afford it. So right here is the ExoScan 3D scanner. It's a handheld scanner that uses 3 cameras and lasers to sort of triangulate the depth and position of the model. It also has self-positioning with a series of accelerometers, so it knows its spot, its location in space, so you can zoom in close, zoom in out, and even stand up to like a whole car. Although this is an awesome thing, the technology behind this is amazing, none of us can afford it. It's close to 100K, and high-end models go up to $500,000. This was probably our biggest inspiration. It's a next engine desktop 3D scanner. What it does is similar to what we're doing. It's a laser scanner. It triangulates the position of the model and gives you a 3D model. It's easy to use, compact, but besides that, there's many disadvantages. First of all, there's proprietary software. The software and tilting mechanism that moves the model automatically is sold separately. So you're looking at 3K just for this module. You want to buy extra software, the works, everything that you need, you're looking closer to 6K. And on top of that, the scan area is pretty small, about 5 by 4 square inch area. So now seeing what's out there, we kind of developed our objectives and specifications. First and foremost, we wanted to develop an easy-to-use desktop 3D scanning device. We wanted to utilize open source software so everyone can contribute to this. We want it to be affordable at the consumer level, max $500, that's what we're aiming for. And we wanted to develop a mechanism that tilts and rotates the model to scan to capture the entire model. And we wanted to get close to 95% of the model surface area. We also wanted to be user-friendly, easy to manufacture since we will bring this to the market eventually. And we wanted full resolution scans to be about 10 minutes max. And our area that we were aiming for was sort of this 10 by 12 scan area. So now we're going to talk about our initial concepts. So when we first started brainstorming, we first were like, yeah, let's make a robot. Let's make a robotic mechanism that had a DLP projector as its end effector, moved around the robot, or moved around the object and scanned it. This had its advantages. It scanned a variety of objects, high degree of freedom, and as well as it would be a cool, complex thing, but there'd be a lot of disadvantages as well. It could be bulky, overcomplicated, and very expensive for the normal consumer.
Our second concept aimed to remove those degrees of freedom. We utilize a rail to move the camera
still get the tilt we want, we still get the spin, but now we have this low profile design, which prevents any obtrusive material appearing in the scans. So this is our final design. Once we kind of tweaked everything, it's basically the same thing as the last one. We just kind of adjusted some things. We found that the triangulation angle between the camera and the laser was too low on our previous design, so we raised that up a little bit. And we also designed more for manufacturability. So we used an inexpensive MDF laser cut, and we also limited glue, so everything can be assembled with bolts and basic nuts, so it's easy to assemble. And this is kind of what we want our motion to look like. Here is this triangle is a laser. It's a line laser. And now we'll focus more on the specific mechanisms within our thing. For our tilting and rotate mechanism, we wanted to rotate 360 degrees minimum. We also wanted to tilt forward and tilt backward plus or minus 30 degrees. That way we can truly capture the model. This is just a simulation of how it would work.
We also have to design a laser sweep mechanism. Basically, the goal with the scanning is that the laser has to be above the top of the model and sweep completely below the model. So we calculated that to be about a 30-degree angle. And another thing with the laser motion that's important is that you need to obtain as smooth a motion as possible. You don't want any jittering. So what we did was we used a regular hobby servo, but we used gear reduction so that we could use the full stroke of the servo while maintaining the 30-degree sweep of the laser. And this video shows kind of the motion dynamics of the laser sweeping mechanism.
The servo's in the back.
Okay, so for our software, we decided to stick with David Laser Scanner, like I said earlier. Again, it uses laser triangulation. It also has within it shape fusion software, which is used to stitch all the pictures together to make the final model. So that way you don't have to buy any other software. You can rely exclusively on David to do all your scanning to final meshing to final model. So again, for our calculations with the laser sweep mechanism, we wanted to get 30 degrees of sweep with 180 degrees of stroke on the servo, so we used a 6-to-1 gear reduction.
And then the calculations for the tilting mechanism, without going into too much detail, we basically needed to know the speed of the motor we need, and then the torque. So we just did a simple gear reduction calculations and ended up with about 1 ounce inch stepper and about 150 degrees per second speed, which is easily obtainable.
Now for electronics, we had 2 Arduinos, one to interface with the user. We used a 4x20 LCD and 4 push buttons. On the other Arduino, we drove 2 steppers, the servo that drove the laser tilt, and as well, we drove the laser module itself with the Arduino. Here's the schematic we used, we put together to interface the LCD. And this is our first video of a full integration test. We use the LCD here. You see a push button menu we're using. We have modes programmed into the Arduino so that we can do a quick scan. We'll see it shortly. It successfully utilized the tilting laser, turned the laser on, and then tilted the model. And it'll tilt it back. As far as fabrication, manufacturability is a big thing. And going along those lines, we designed this so that it can be printed all on one sheet. You can see individual modules that make up our components. For example, this is you can see this in the upper right corner right there. And that's one mechanism. And these are the parts blown up and then laid out. This is the tilt mechanism. Even the gears and that railing, it's all cut. The only thing we bought in terms of hardware were bolts. Same thing.
All right, so you're asking yourself, where's the proof? Does this thing really work? several challenges. First, he's really big. He's about 6 by 8 or something like that. He has large, round edges, and they're reflective, which makes it difficult for the laser to pick up because the laser gets reflected off of the edges and diffracted out, as opposed to coming back to the camera. Here you can see the computer scanning, and in a second here, Cartman's going to show up. And that's just after one pass. We already have a pretty decent model. This is one of our early scans. With further refinement, you'll see that we actually got better at scanning as we went along. The next test that we did is a digital multimeter. Again, it poses several challenges. First, you have the very flat surfaces that are also reflective. The screen is reflective, as well as this lettering. So it poses challenges for the laser scanner to capture the data, but still, here you can see it still gets pretty good definition, even gets the indentation of the letters. Our final scan is probably the most difficult scan of all. It's the Hulk, and it poses several challenges. First of all, you got a green laser on a green object. That's one disadvantage. Second is he has a lot of different curves at different angles, and he has several surfaces that are hidden behind other surfaces. So this is a pretty difficult scan. Basically, these are all the poses that we captured. This is the photogrammetry side of David. Again, David scans with the laser first, then it takes a picture and applies color data to your model. And here is our final model. As you can see, it catches the definition pretty well. I mean, it's got some nice six-pack right there. And here's the actual model that we scanned, and here's our 3D mesh that we came up with. Pretty close and a pretty good scan, I would say. Now, the most important thing is bringing this to market. So we made a little video that we're going to use to try to sell our product to you.
So in this part of the video, it kind of runs through the different modes. You see, sweep the laser there manually. There's our so we're running the different We're running the different modes right now. This is our quick scan mode. It's sped up, but it basically takes 6 scans. This is our software integration. This is our model, just after one pass, that we've already captured. That's the scan. Yeah, that's the ScanBOT.
So in conclusion, we were able to successfully build a mechanism that can scan simple objects, the Hulk, the multimeter, the Cartman. Our full scan actually came in under 10 minutes, and the biggest thing, it cost less than $300, well under $300. Future work, firstly, we would like to develop software that would automate this process. For now, the biggest thing is stitching those meshes together. Next, increase manufacturability so that it wouldn't be a simple, wouldn't be like a do-it-yourself thing. It would maybe take 10 minutes to put together. And lastly, marketability. We want to sell this thing. The market is ripe. There's brick and mortar 3D stores, 3D printer stores now. This is just open market right now. We'd like to thank Dr. Lindsay Du, our senior advisor. Dr. Furman, we're using his laser scanner to cut most of our laser cutter to cut most of our acrylic and wood. And Mike De Silva for
take for actual full scan? Like how long did it actually take for the full scan of the Hulk to come out?
Well, the scan itself is pretty quick. The full scan, you can get it in, like we said, under 10 minutes to go through all return positions.
And
It's the-
editing and stitching
It's
and
the
all.
post-processing. Like, how do you tell a sculptor when he's done? You know, you never know when you're done. You can take it as far as you want. So I think, how long did it take you? Like
The computer, even the computer just processing by itself, probably 30 minutes to an hour, because it's running over 100 iterations of mathematics to mesh all the 3D data together. And you can imagine, unless you have a supercomputer, it takes a long time.
I was gonna ask if you guys have thought about maybe like a version of this kit that doesn't include major pieces of hardware like a camera and laser, so people can maybe get their own higher definition camera if they want.
Yeah, well, one of our goals when going to Kickstarter, we're also going to make this, like we said, open source. So we're going to put all the design files, all the laser gun files, accessible to anyone who wants to cut it, build themselves, add to it, adjust, etc. Put their own kind of camera, their own laser, whatever they want.
How long was the program? Like programming, like the codes? You guys,
How long did it take to do it? Or
like how large, like the lines of programming?
I didn't count.
I know, but I mean,
500.
At least.
At least,
So if you were to like make it for a bigger model, this is gonna scan 10 by 12, right?
Yes.
If you want to make it like,
With a better laser.
you can-
This unit itself right now, you can put your face behind the last edge there, and it'll capture it. There's a method where basically after you calibrate it, you take the panel out, and it can scan anything as long as the camera and the laser are in the same position. So if we had like a much better camera, you could theoretically you could scan this whole table from that distance.
What about the possibility of like stitching multiple scans together, like with some type of reference point on the object? So you get like high resolution close-up scans in one part and then another part and another part.
You can do that.
Software.
It's completely up to you what part of the scan you want to use. You can just select a certain part of the scan, but it works better with more overlap. So like say you get his arm in 3 different pictures, it'll probably use the arm to relocate them.
Does your mechanism have to be in a black box where it's preventing light coming in for it to work more efficiently, or do
It
you?
actually works with this kind of lighting, because it needs to take a photo of the object. You can do, basically you just set your camera shutter length
Okay.
and to adjust for your lighting conditions.
just exposure, etc. So you could use it anywhere. It does help you in dark a little bit, but if you make the right adjustments, you can do it in this room or maybe even outside. More questions?
We're gonna go from running.
Just real quick, show you guys the mechanism.
Just the motion of it. We don't have an interface to the software right now. So this is the quick scan mode that you showed. You can see here the laser sweeping the model. Rotates to